Okay, so we'll start our lecture today. So this is Physics 2051, Quantitative Methods for Basic Physics. So I'm the lecturer, Dr. Makolai. What I'm showing you now is the course outline. Okay, so the course outline can be found on Blackboard. Okay, so basically everything about this course will be uploaded to Blackboard. Okay, so the course outline is here, which is just the same as what I'm showing you now. So this is my contact information. Okay, first of all, please pay attention to my consultation hours. Okay, so I have 2 time slots every week. Okay, so Monday 3 p.m. to 4:45 p.m. and then Wednesday same time 3 to 4:45 p.m. Okay, so that means at that times I will be sitting in my office, and then you can just come to my office if you have any questions about the course. And on Wednesday I also give you one more option, which is Zoom. So that means I will still be sitting in my office, but at the same time I will open a Zoom session. Okay, in case some of you are not able to come to campus because of sickness or quarantines. On Wednesday, you can either use Zoom or face-to-face. So the Zoom link for this consultation hours, again, can be found on Blackboard. So you can see this Zoom button here, and then you'll see my link for the consultation hours every week. Okay, so for example, today 3 p.m. Okay, next Wednesday 3 p.m. and so on. So, and of course, if you are not available in these 2 time slots, you're always welcome to try to find me at other times. Okay, so unless I'm teaching or I'm in a meeting, okay, most of other times I'll be in my office. You can just stop by and see if I'm there, and I'm happy to answer your questions. Alternatively, you can also send me emails. Okay, so here let me introduce our TAs. So okay, so good. All 3 of you are here. Okay, so Mr. Fong, Sam, over there. So he was the TA for the same course last year, so he did a very good job, and so I'm happy to have him again to be the TA. And Mr. Poon, Jason. Okay, so first year to be the TA for this course, and then so you are year 1 MPhil student, right? Okay, so and then Kevin. Okay, Kevin back there. Okay, so last year he was the TA for classical mechanics physics 3011. So I believe most of you will take this course in term 2. Right, so again, he did a very good job, and good to have him for this class. So you can see the information here, like consultation hours, emails, and also their office location. Okay, so if you have any questions, you can ask me or ask them. Okay, so and so they will be responsible of the exercise classes every week, and also grading your homework assignments as well as the midterm test. Okay. So so right now, all the exercise classes and their consultations sessions will be in face-to-face mode. Okay, but it depends on situation. If I realize that some of you may not come to campus, again, as I said, due to sickness or due to quarantine, then I will consider also have their consultation hours in Zoom mode as well. Okay. But this is the arrangement for now. Okay. Okay. So Sam and Jason and Kevin, you might leave if you have other things to do. Okay. So these are just the information for our lecture, right? Lecture location and time, and then exercise classes, location and time. Okay. Okay, so these are the reference books that we'll be using. Okay, same as last year. And actually, for the second one, you can actually find an e-copy from the library website. Okay, so you can just download it from the library website. Okay. So here, if you need some supplemental learning materials, so on some very basic elementary math concepts, if you have forgotten or if you have not learned before, try to go to this page. Okay, several years ago, the department set up this page to make several videos on different basic math concepts. Okay, so this is the assessment scheme. Okay, so 24% go to homework, 34% go to midterm, and 42% go to final exam. Okay, so we will fix the date of midterm by next week. So here I list the course contents. Okay, so you can see that we have quite a number of different topics, and they all will be useful in different areas of physics. Right? So you'll see these mathematical skills again in different courses that you will be taking. Okay. So actually, I believe majority of you might have already taken math 2530, right? So that advanced calculus. So there will be a little bit overlap between that course and this course. So mainly on the first topic, partial differentiation, and also some contents on Taylor series. So the approach of this course will be quite different from the course offered by the math department. Okay, so there they focus on rigorous proofs, okay, and proving the theorems. So here, most of the time, we don't discuss the proof rigorously. Okay, so most of the time when I talk about some theorems, I'll just give you some geometric intuition on how that works and why that works. Okay, but we'll skip most of the rigorous proofs. Okay, but if you're interested in the proofs, I can always suggest you to which reference book to look for those proofs. Okay, so So let me just say a few words about different topics. So first topic is the review of partial differentiation. So as I said, so this is a topic that you have already learned in your advanced calculus course. And so this one will be quick. I think we'll finish the first chapter maybe within two days. But for those of you who haven't learn this topic, you also don't need to be concerned because I'll give you enough examples to give you practice. Okay. So then the second topic is about multiple integrals. Okay, so you are doing integrations for function of two variables or even three variables. Okay. So actually, for this topic, I believe you need to use immediately in your other course that you are taking, the 2041. Okay, when you learn E&M, if you want to do integral over a charge distribution, finding the electric field, you need to use this multiple integrals. So I believe in that class, okay, so I believe Dr. Tong will also give you some brief introduction on how to do multiple integrals. So the third one is vector calculus. Again, this would be a topic that will be directly applied to your E&M class. Okay. So and then the fourth one is the ordinary differential equations. Okay, so again, you might have already learned a little bit about this in your advanced calculus course, but here we focus more on the examples in physics. Okay, so in mechanics or in some electric circuits and so on. Okay. So the fifth one is the infinite series. Okay, so power series and Taylor series. So you, whenever you make approximations, you see Taylor series, right? So this will be a skill that you need to learn for many courses that you are going to take. Okay, finally, we also have the topic on matrices. So we'll consider the different kind of matrix, and then most importantly, you know how to find eigenvalues and eigenvectors of a matrix, and what is the geometric or physical meaning of eigenvalues and eigenvectors. Okay, and so the last topic about complex number and complex functions. So according to experience from last year, we might not have enough time to cover that, but we'll see how it goes. So finally, so for assignments, submission and collection, we'll just use a Blackboard. Okay, so for this course, you'll probably have about 9 to 10 homeworks. Okay, so in total. And for the late submission, okay, some marks will be deducted. Okay, so I'll tell you the exact scheme when I release the first homework. So finally, about the academic honesty and plagiarism. So this is something that I need you to do is, I'm sure that you've done that before, is to sign the declaration form for the academic honesty. Okay, so here I put the form on Blackboard. Okay, so you just read it, sign it, and then submit it here. Okay, submit it through a Blackboard. So one more thing. So right now, so you can see that I'm actually using Zoom to record lectures. So I will do it for all lectures. Okay. So what I will do is that I will upload the link to the video on Blackboard. So in this folder. Okay, but there's a time limit. Okay, so for example, if I upload the video for today, this afternoon, okay, then I'll remove the link after 10 days. So that means next Saturday, next Sunday, I'll remove the link for today. Okay, and that same process repeat again. Okay, so the purpose of this making the videos, first of all, for you to do revision, and then second is that as we may notice that some students might get infected and need to be quarantined And then for those cases, they will still have access to the contents of the lecture. But again, remember, every videos will be kept there for 10 days only. Okay. So I wish you follow normal schedule to learn the materials. I don't want you to just keep all the videos and then study the night before midterm. So that's the purpose of not keeping the videos for too long. Okay. Okay, so at this point, are there any questions about the general arrangement of the course? Okay, if not, let's just start with the first chapter. Okay, let's just start with the first chapter. So other people also have the same problem? Okay. So I need to take a look. Why is that? Oh, that's why. Okay. So what about now? Is it okay now? Yes. Okay. Good. Good. Okay. So that's good. You can get the chapter 1 lecture notes. So actually I made some minor update this morning. So it's good that you download this right now. Okay. Okay, so chapter 1, review of partial differentiation. So I add the word review because, as I said, I believe majority of you have learned this topic already. So might be a bit boring for some of you, but I hope it will just be a good revision for you. And for those, again, for those who haven't learned about this topic, okay, I will give you enough example to catch you up to speed. Okay. Okay, so partial differentiation. So first of all, we know from high school that the meaning of derivatives or the meaning of differentiation, right? So suppose I have this function of one variable, right, where I draw this curve to represent this function in this graph, right? So then if I take the derivative, or if I do differentiation on this function, so the meaning is that you consider some value of x, right? And then you draw the tangent to the curve at that value of x, and then the derivative means the slope of this tangent line, right? So that's what it means by derivatives, okay, geometrically. Or we'll say that this derivative df dx means the rate of change of this function with respect to x. So that's derivative. That we all know that. Okay, so now what about partial derivatives? So what we are considering now is a function of two variables, right? So, or later it can be function of even 3 or 4 variables, but at least for function of 2 variables, we can still draw it in a 3-dimensional space, right? So this is an example here, function of two variables, f, x, and y. So f, x, and y, so that means at any pair values of x and y, so you could imagine that you have this xy plane, so each point is represented by coordinates, right, xy coordinates. So at any points on this xy coordinates, so you have some value z. Right, so and then if you change to another coordinate, you may get another value of z. Right, so then graphically, if you want to represent this function of two variables, right, so what you end up getting is a curved surface in this three-dimensional space. Right, so for each point on this xy plane, I have some certain value of height by which I use z to label it. Right, so then at the end, I get this curved surface. So in fact, this curved surface, okay, is constructed by is representing this function, okay, x squared minus y squared. So this is a function of two variables. It's a very simple example. So now we want to take derivatives. So that means we want to find some kind of slopes, and we want to find how that height changes as we change the position. Right? So that's the idea. Right? But for the derivatives, right? So there's only one direction you can go, right? So you move along the x-axis. So you can either increase x or decrease x, decrease x, right? So there's only one choice. But here you have this entire xy plane that you can move along. So then here we have we have two cases. Okay. So the first case is that I am keeping x. So suppose I am at some point in the xy plane, and then I'm keeping x as a constant, and then move along the y direction. Okay, so just like this plane here. So suppose I'm here, and then I move along this blue plane, right? So I'm changing y, but my x position is fixed, right? So this plane, right, represent the region where x is fixed, right? So if you do the intersection, right, between this plane and your curved surface, then so you cut it and then look at the cross section, right? So basically what you see is a curve like this, right? So it's a curve that concave down. So now what you see, so in your world, so what you see is a curve now. So that means you are effectively, if you are keeping x constant, now you effectively keep seeing a curve. That means you're effectively seeing just like a function of one variable. So then now with this curve, then you can take derivatives, or just like what you did with function of one variable. Right? So then this operation that we call this the partial derivatives, and this is partial derivative with respect to y, right? Because I'm keeping x fixed, and then I change, I treat y as a variable. So this symbol partial f partial y. Okay, and then I have this subscript x means that we are keeping x as a constant. Okay. So later on, or when you see some textbooks or even some physics problem, usually you don't see the subscript x, or sometimes you don't see the subscript x, because it's understood that when we take the partial derivative with respect to one variable, then we are keeping the partial derivative, we are keeping the other variable fixed, right? So in some books you will see that this subscript x is not even written, but here just to remind ourselves. Okay. Actually, especially in thermodynamics, actually it's important to keep the subscripts, because otherwise you get confused pretty easily. So then this partial f partial y is the slope, right? So of the tangent to this curve. So now you could imagine that in this picture, I am keeping x at say -10, right? But you can always pick another constant value of x. So let's say you can translate this blue plane to another place, or you translate this blue plane, and then you can still do the cutting and see the curve. So in this case, because this example is simple, you realize that even I translate this plane left or right, I'm not rotating the plane, I'm just translating the plane left or right, you always see the same downward concave curve, right? So, but anyway, you will be able to take your partial derivatives, right? So, and so this is, although this is a trivial example, so but let me just do the calculation, right? So how do we do partial f partial y? So if I do partial f partial y, so that means I'm taking the partial derivative of x squared minus y squared, right? And then what you do is that, as I said already, you are treating x as a constant, right? So that means that the first term is just 0. So you just need to take care of the second term. Right, so then you get -2y. Okay. So now let's consider the second case. This time, I am keeping the y variable fixed. So see this green plane, and then I'm moving along the x direction. So basically what I'm doing is that I take this green plane and then again cut this curved surface and then look at the cross section. And then this time I see a curve, but this curve concave up instead of concave down. But the same idea is that you have curve and then you take the derivatives, right? Pretending this is a one variable function, right? So in that case, if you take partial x squared minus y squared, so this time you just treat the second variable to be a constant, right? And then you just have 2x. So you see that, so I have a function of two variables. So after taking the partial derivatives, I still have a function. I still have a function of y or x. And because this example is simple, so it so happened that after taking the derivative, you either only have y or only have x. But you could imagine that for more complicated functions, which I will show you in the next slide, if you have a function of two variables, after taking the partial derivative, in general, you should still get back a function of two variables, right? And expressions which contain both x and y. Right? So, for example, let's see here. So this function, this time I'm looking at f(xy) equals a product of two sine functions. Okay, sine 2 pi x and sine pi y. So let's see if you could intuitively understand why the function looks like this, right? So it looks like you have a mountain here and then you have a valley here. So again, just to get some idea is that, again, if you try to fix one of the variables, right? So let's say if I try to fix this y variable as some particular y naught, right? Then this will be just a function of, well, it will just be a number, right? So some number. So then what it means is that I can, for some particular y value, what I have is some constant times this sine 2 pi x, right? So it's just like some amplitude, right, for this sine function, right? So let's say, for example, if I if I make a plane here, right? So if I try to draw a picture, so I have this is Z, this is X, then this is a sine curve that I have. Right. So now if you imagine that you translate the plane, so that means you select another constant y value. So suppose I translate the plane to somewhere here. So now if you want to see the cross section this time, you still see a sine curve, but then this time the amplitude is smaller, right? So for different, if you just translate to different position, you always get this sine curve, but with different amplitude. So you can try to do the exercise by yourself for the other dimension, right? So if you cut it the other way, so what you will see is just a half of the sine curve. So now let's take the partial derivatives, right? So if I do partial f partial x, right? So then all you need to do is that you just treat this part as a constant, right? And then you just need to take derivatives for this sine 2 pi x. That's why my partial f partial x is just 2 pi times cosine 2 pi x times sine pi y. Now if you draw it again, you of course still see a curved surface, but it looks different because now it's a cosine times sine, not sine times sine. Okay, but anyway, you see that this is a function of two variables still, right? So similarly, if you take partial f partial y, right? So this time I have sine 2 pi x times cosine pi y. So another curved surface looks different. So then this is the first order derivatives, right? So and then in principle we can take the derivative again, right? So I'm sure that at least for single variable calculus, you've learned what it means by a second order derivative. That means you take the derivative and then take the derivative one more time. So then I have these two pictures, same as the slides, previous slides. Then if I take this and then I take a partial derivative with respect to x again. So this is the symbol that we are going to use. So, and then what you get is a curved surface like that, right? So it looks like this. So on the other hand, if I look at this function and then I take the y derivative again, then this is what it looks like. Okay. So there is also one more choice, right? Is that I take this, but the second time I take the derivative, I do not consider the same variable. Right? I consider, so the first time I take derivative with respect to x, and then the second time I take derivative with respect to y. So this is the symbol that we use. Alternatively, for the other case, so this is the first time I took the derivative is with respect to y, but then the second time I took the derivative with respect to x, then I use this symbol. So, and then you find that they are given by this. Okay, so they are actually the same. The order doesn't matter. So, and you know that so to be more rigorous, so you might have already learned that the for this to be true, okay, so for this order to be for the result to be independent of this order, okay, so you need to satisfy the condition that first of all both of the first order derivatives, okay, have to be continuous, and then also these two derivatives, if they are also continuous, then it is guaranteed that the order doesn't matter. So and in practice, in most of our physics problem, okay, we we do deal with continuous functions with continuous derivatives. So most of the time, you don't need to worry about whether this one and this one will be the same or not. So most of the time they are, at least in the physics problem that we are considering. So just now, I used the most common way to represent a function of two variables. That is using a curved surface in the three-dimensional space, right? So because that's the easiest way to see how the height change as a function of space, right? So, but here I want to also tell you that there's another way to represent a function of two variables, right? So if you have been hiking before, I believe you might have seen this kind of picture on a map. So this is known as a contour plot. Okay, what it means is that, so suppose I have a function of two variables, okay, so which represent the height of a mountain at different coordinate points. Then of course, as I said, the most common or most direct way is to actually draw the morphology of this mountain, right, as a function of position, right? So this is what you have. You imagine this is a three-dimensional picture, right? So now you can see that I have these lines on these mountains. So they are known as the contour lines. So what it means is that, so suppose you see this line 40. So that means if you are going on a hiking, if you suppose you are walking along this curve, this line, then your height, your height from the ground, okay, is always 40. And then if you are walking along this line 30, so that means, again, so similarly, that means that the distance between the ground and the vertical distance between the ground and you is 30. So same idea for the 20 and 10. Right? So of course, you can always draw more of them. You can draw a line maybe somewhere between here to indicate the constant vertical distance of maybe 15. Right? So now the key is that I have all these contour lines, and then I can project all these contour lines on a two-dimensional map. So a two-dimensional paper, right? So a map on the paper. So then you see all these contour lines, right, on this paper, and this is, as I said, this is something that you have seen on the map. So this is known as the contour plot. Contour plot. So this curved surface is something that you have just seen. So if I make the contour plot, okay, it will look something like this, right? So suppose you're at this point, right? If you are walking towards the positive x direction, so that means you are from here to here. So then you see that you are crossing some lines, right? So you're crossing a line with 100 and then 200, 300. That means you are crossing these lines, which indicates that you are going to the upper and upper level, right? Similarly, if you go to the negative x, then you are moving this way, and then you're crossing these contour lines with higher and higher numbers. Okay. So on the other hand, if you are, again, from the origin, if you're walking along the negative y direction right here, then you are going through all this number with more and more negative values, right? So you're going down. So one thing that's interesting and might not be so obvious here is that if you are walking along this line, this diagonal line, then your your vertical distance from 0 is always the same. So you are not going up or going down. You are just going in the horizontal direction. So this is just another simple example. So this one looks more like a mountain, right? So I have this constant minus x squared plus y squared. So then you can see that all the contour lines are circles, right? They are all concentric circles, right? The one that is smaller has higher number because the one that is smaller is closer to the center, which is the peak of this mountain. And then as you go further and further away, then you have larger and larger circles with smaller and smaller numbers. Okay, so this is just one thing that for those who are interested in programming, so you might and if you're interested to make these plots, okay, you can consider taking a look at MATLAB. Okay, so MATLAB is a software for scientific computing. Okay, so if you have learned C before, I think MATLAB would be straightforward to you to use. And this is so as long as you are a member of CUHK, then you're free to download it from the ITSC website. Okay, so I made all these plots using, well, not this one and these using MATLAB. Okay, so now again, I have a few simple exercise. Might not need to go through every single details, but just to at least remind you how to do partial derivatives. So in this exercise, okay, so I have this function which is known as the two-dimensional Gaussian distribution. So if you don't have the y square here, right? So I believe that is the Gaussian function that you have seen before, right? So then if you don't have the y here, basically you have this bell-shaped curve. So now I have this x squared plus y squared. If I draw it out, so it looks like a bell, right? But in 3 dimensions. So now if we want to find the partial derivatives, okay, so how do we do that? So again, it should be straightforward, right? Because as I said, the way we do partial derivative is that I have 2 variables. Then if I take the partial derivative with respect to one of the variables, then that means I need to pretend that the other variable is just a constant. And then I just do the derivative as if I am just working with a 1-dimensional function. Right? So, okay, so then then these should be quite straightforward. So I'll just try one of them. Okay, so let's say I want to take the partial derivative with respect to x. So then I will use chain rule, right? So chain rule. Then I'll just first write down the exponential function. And then I take the derivative of this expression here. So then now as I said, I pretend that y is a constant, right? So then what I have is just times minus x divided by sigma squared. So that's it, right? So in fact, if you want to take the derivative with respect to y. Okay, so you might realize that you don't need to do it over again, right? So if you are taking this with respect to y, you realize that at the end, well, because of this, you can see that the symmetry of this problem, right? Because if you interchange x and y, then everything are the same. So what you need to do is just that you just need to replace this x with y and then replace y with x in this case, right? So, and then this is what you got. So second order derivatives, I won't do it here because just following the same procedure, right? So I have this first order derivative already, and then you just take the derivative one more time, and then you get your second order derivative. Okay. So when do we see this kind of function? Okay. I would say you may see it in many places, but one of the physics example that I can give is that a laser. Okay, so if I use a laser pointer to shine the laser light on this screen, right, you see a dot, a bright spot, right? So maybe too bright for your eye, but you can roughly determine that this is like a circular dot. And in fact, that kind of laser dot, okay, so if I want to ask the brightness of that spot, right, at every point in that spot, but that spot itself has a size, right? It's not just a point. That spot itself, it really is occupying a circular region, right? And if I want to ask what is the brightness distribution of that laser spot, and in fact, it will roughly follow this Gaussian function. So that means the center is the brightest. Well, that's unsurprising. And then you have this decay, okay, as you move out from the center to the other side, to the outer side. Yeah. So here, I just assume that this standard deviation is a constant. So this standard deviation is not a function of x and y. I'm not sure. Maybe you can give me your example, okay? But in many cases, so standard deviation is just characterize how spread out that distribution is, right? So that standard deviation should not be a function of x and y. It should be a number to characterize how spread out that spot is, okay? But no matter what, okay, if you suppose you can find an example that sigma is in fact it's a function of x and y, then yeah, you can still do the partial derivative, right? So but you just treat this one as a more complicated function, right? And whenever if you just take partial derivative with respect to x, then again you just always treat the other variable a constant and then do your job. Okay, so the other example, and in fact, maybe in year one physics course, you have learned about waves. Okay, so in this case, I am talking about standing waves. So what I want to say is that previous case, when I talk about function of two variables, I always use this surface, right, with this two, with this xy, to as the two-dimensional space to draw my curved surface, right? But sometimes, even if we use, even when we have these two variable functions, we may not just draw the function like this. So that's just maybe other more intuitive or physical way to represent this two-dimensional, two-variable function. So this is an example, right? So if I have a standing wave, which is a function of two variables, okay, I have this sine kx cosine omega t, right? So then the way we represent it is that we can make a movie, right? So at t equals 0, maybe the string is like up here, right? After some time, it will become flat, and then after some time, it will bend down, and then after some time, it become flat again, right? So this is a function of two variables, x and t, right? But in this case, because we want to show the variation in time, right? So it's even more intuitive to show it as a movie, right? Instead of really treating x and t to be two axes and then draw a curved surface up there, right? So then, but anyway, even in this case, if I want to take partial derivatives, then the idea is really just the same, right? So and so I'm not going to do it here, but one thing that you can verify by yourself is that you see that the second order partial derivative with respect to x and the second order partial derivative with respect to t has a certain relation, right? This is the wave equations. And again, this is maybe something that you have seen in your first year mechanics physics class. But here you can verify that this is indeed the solution of this equation. This is known as the wave equation. So okay, so I think let's take a 10 minutes break. Let's start again at 12:35. Okay, 12:35, and then we'll continue. So if you have any questions, you can ask now. Okay, so let's continue. So just now I gave you an example on this standing wave, right? So and then there's another type of wave which is known as the traveling wave. Right? So in standing waves, you see that if you fix both ends, and then this string will just vibrate up and down, up and down. And then now this traveling waves is that if you take a waveform at a particular time, it looks like this, right? So after some time, right, the peak of this wave is shifting, right? Shifted to the other position, right? So after some time, again later, so the position of the peak shift again, right? So this type of wave is the traveling wave, right? So the traveling waves mathematically can be expressed in this form here, right? And you realize that again, if you try to take the partial derivatives with respect to x and then with respect to t, you realize that it satisfies the same wave equation. So both standing waves and traveling waves are the solution of this wave equations actually. So, and another a remark here is that I have this sine kx minus omega t. Okay, so if I have sine kx plus omega t, okay, you easily verify that is also another solution of this wave equations. But physically, what happened is that in that case, the peak of this wave is shifting to the left over time. So instead of shifting to the right. Okay, so this is basically just a wave propagating in the opposite direction. So even more complex is that actually I can have this wave in 2 dimensions. So what I have here is not just a string, but imagine that this is a membrane or the surface of a drum. Okay, so what I'm showing you here is that this membrane or this elastic surface is vibrating up and down as a function of time here. So in this case, okay, the wave is not really traveling anywhere, right? So just imagine that all these boundaries are just fixed. So the wave is just go up and down. So this is a standing wave again. Okay, but now I am describing a membrane instead of just a string. So here, if you try to take the partial derivative with respect to all these 3 variables, and then you'll find this, you verify that this relation is satisfied. I think there's a typo here. There's a typo here, because this should be y. So this is a 2-dimensional wave equation. So I believe if you go to the course 3051, okay, so wave equations is one of the major topic in that course. Okay. So now that's so I believe all the exercises are very standard and straightforward for you. Okay, so then the other important concept is about the extreme values. So again, for single variable calculus, right? So you know how to use derivative to find the extreme points. So extreme, that means that it is either maximum or minimum, or actually it can be neither maximum or minimum, right? So for this single variable function, right? So this one is a maximum, right? So and then you might have this one is a minimum, right? But it can be neither. So for example here, so this one. So but in all 3 cases, so in single variable calculus, in all these 3 cases, I have the first order derivative at these points to be 0, right? But then the difference is about their second order derivative, right? So now for function of 2 variables, so we want to do something similar. Okay, so we want to have a way to find whether this point is a maximum point, a minimum point, or this the third one, which we call a saddle point. So it's neither a maximum or minimum. So then I have these 3 functions. So graphically, you know what happened, right? So maximum, minimum is very clear. And again, the first condition to satisfy that's first of all their partial derivatives. So their partial derivatives has to be 0. Okay, so both partial f, partial x, partial f, partial y has to be 0. So then this is a local extreme value, first of all. Right? So then the second derivative test is to tell us whether this local extreme value is maximum, minimum for this saddle point. So the way to do it. So if we think about it, if I just not look into this formula for a moment, if I want to find whether there's a maximum or minimum, you might think that you have to try to consider different directions, right? So you are at the peak of the mountain. So how do you know that? You need to, for example, walk to the right, walk to the left, walk to the north or south to make sure that you are always going downward, right? So then you know that you are at the maximum. So similarly, if you're at the minimum, you need to again try different directions to make sure that you're always going up. Then you know that you're at the minimum, right? And then if I'm at this point and you realize that in one direction, if I walk along the x direction, I'm going up, but if I walk along the y direction, I'm going down, then I know that this is neither a maximum nor minimum. So so it seems that you need to try different directions, but at the end, basically, you just need to satisfy these conditions. You are not going to need to take the partial derivative along some arbitrary direction. This is not, luckily, this is not what you need to do. But why is it the case? So why do we have this seems to be funny looking expressions here? Okay, so at this point, so again, I believe you have seen this formula in your advanced calculus course. Okay, so here I would like to explain more. So in this course, but we have to wait until chapter 5 or chapter 6 when we talk about eigenvalues, eigenvectors, and also the Taylor series for the two variable function. When we get there, it will be more transparent why these formula works. Okay, for us to distinguish maximum, minimum, and saddle point. Okay. So for now, let's just accept this formula. Okay, so we'll come back to this later. So next, I want to talk about the differential and total differential. So suppose in the case of a function of one variable, okay, so again I have this curve, and I start from this initial value of x, and then I change the value of x to here. So I have this change in delta x, and then I want to ask, what is the change of the value of the function? So what is delta f? Right. So then, of course, the most precise way to find delta f is that you know the function at this x, and then you know the function value at this x, and then you know the function value at this x, and then you just subtract them, then you know exactly what delta f is. Right. But there is an approximate way to find the change, okay, without precisely taking the value of f of x at this point. So suppose, okay, just imagine that I know the behavior of the function here, but I don't quite know what happened here. Then how do I estimate if I move the value of x by this amount, then how much the function has changed? So what we can do is to use the derivative at this point. Okay, so because this, you can see that this tangent, right? So although the slope, this is just a straight line, right? Although it won't be perfectly overlapped with this curve, right? But as long as the delta x you are considering is small enough, right? So then this delta f, this change in the function value, will be approximately equals to this df dx, which is the slope of this tangent line, times delta x. Right. So then now I want to consider the same question for function of two variables. Okay, so this is a small section of my function of two variables. You imagine that this is small part of the curved surface that I have for the entire space. So suppose initially I'm here, right, at some value xy, and then I change the value of x by delta x, and then I change the value of y by delta y. So then I will be up here. So, and then I want to find, so how much is the change of height, or how much is the change of the function value? So again, if you exactly know the function everywhere, then you can just plug in the new value of x and y, and then you know how it goes. But again, I want to just use the value here and then use derivative to estimate how much I change. So without explicitly knowing the exact height at this point. Okay. So it turns out that to do that, we can just sum the contribution of the two changes in the two variables respectively. So what I have is that my delta f, so which is this, basically this delta z, is actually given by partial f partial x delta x plus partial f partial y delta y. So you just add them together. So it turns out that it's quite convenient. Okay. So here I can just go to the appendix and just geometrically very roughly show you why it works. Okay. So why is it so simple? Just one more variable, just do a simple sum. Then you can basically find the value here. So if I just quickly go to the appendix chapter. Right, so again, this is just a very similar picture here, is that I start from this point, right? So and then I change x to x plus delta x, right? And then I change from y to y plus delta y. So this is my endpoint, this is my starting point, and then this is my final value of this function, and then this is the initial value of this function. Okay. So the change in f, I call it df or delta f, is just given by this. So it's exactly given by the subtraction, the difference between these two values, right? But I want to show that. So this one is just approximately given by this simple sum of these two terms. Okay. So what we need to do is really to consider this as a two-step process. Okay, so how do I get from this blue point to this red point? Right, is that my step one is to move along the x direction, along the x-axis by dx, right? And then my step two is to move along the y-axis by the small distance dy, right? So then I get here. So then my step one, so you can see that this is the face of this object. Okay, so I just draw it here. So and then another face of this object, I just draw it here. So for step one, okay, so I'm basically going from this point to this point. So for step one, the height change is given by this little vertical side of this small triangle. Right? So and then for step two, Okay, so and my height change is again given by this small vertical side of this triangle. So then that means I need to sum up this dz1 and dz2. So first step is that I am keeping y to be constant. I'm keeping y to be constant. So that's why my dz1 is just given by this partial derivative times this dx. Okay. So my step two is that I keep x constant by moving along the y direction. So that's why this dz2 is just given by. So this formula is just from the single variable calculus, right? So because I'm pretending just have one variable. So then now here, the second term, right, the dz2 is given by partial f partial y dy. But there's a slight problem here, because from this point to this point, I am evaluating my partial derivative at this point. Okay, but in the second step, because I've finished the first step already, because I'm here already. So in the second step, when I take the partial derivative, I am, in principle, I'm taking the partial derivative here, but not here. So that means when I take the partial f partial x, I'm evaluating that at this point. But when I take the partial f partial y, I'm evaluating that at that point. So that should be small difference. But however, because this distance is small, so I just say that this partial f partial y, so evaluated at the second point, is basically given by the partial f partial y evaluated at this also the same original point plus some small number epsilon. Okay. But this epsilon times dy, so two very small number multiplied the product of these two small numbers just go to 0. So then at the end, I can just ignore this. So then at the end, my df or my dz is given by this dz1 plus dz2. Then I have these two terms summed together. So then this is just a simple sum of that two terms. So then this df is what we call the total differential. Okay, the total differential. So now some examples. So I want to use the total differential to find the approximate change of a function. So actually the first example is just a function of one variable. So I want to find, so suppose I have this volume of a sphere. So the initial radius is this capital R. If I change the radius from R to R plus delta R, so then how much the volume of this sphere has changed. So again, if you want to be exact, want to be precise, what you just need to do is that you use R plus delta R as a radius, calculate the volume once, and then you subtract that with the original volume. That's the most precise way to do it. But as an approximation, so what you can also do is that the delta V, which is a function of R, is roughly given by this dV dr times delta R. Right? So then this is just 4 pi R square delta R. And so you are not actually calculating the volume twice and then subtract. Now you're just using this differential. So geometrically, this is also easy to understand, right? Because this 4 pi R square delta R, right, roughly refer to the volume of a spherical shell, right? The volume of a spherical shell. So you could just imagine that if you change the radius a little bit to this R plus delta R, so then this volume is just roughly given by the surface area times this thickness. right? So that's why it's 4 pi r squared delta r. So geometrically is intuitive to understand. So this is one variable, right? So then two variables. So now we are considering the volume of a cylinder, right? So the volume of a cylinder depends on the radius and also the height. So this is function of two variables. So now same question, but this time I change r and I also change h. So from r to r plus delta r, and then from h to h plus delta h. Then I want to ask the change in the volume of the cylinder. So then if you apply this formula for the total differential, okay, so you just have two terms, do a sum. And then geometrically, again, how do we interpret this? So for the first term, you realize that this is actually the volume of a thin cylindrical shell. So that means if I increase the, so I'm exaggerating the, so then increase, then the change in the volume is given by the volume of this region, right? So the volume of this region is given by this thickness times the surface area of that of this cylinder, right? So that's why it's 2 pi r h times this delta r. So then the second contribution is that I increase the height, right? So I need to add this part. So then this part is a disk, a circular disk, right? And that volume of a thin disk is just given by pi r squared times this change in the height. So this total differential can be generalized to even more variables. So we have been considering just two variables, but if you have 3, 4, 5 variables, turns out that you just need to keep doing a linear sum for all the terms. So then that's so much for the total differential. Then the next one, which I think the concept might be a little bit challenging. It takes some careful thinking to clear up, is the total derivatives. So here, suppose I have a function of two variables, like x and t. So then the total differential, now you know this is how it should be written. So then the total derivative, okay, the total derivative is defined like this. So the total derivative of f with respect to one of the variable, time, is written like this. So basically, what we are doing is just divide both sides by dt. Okay, so then you get this so-called total derivative. So, but then there are questions. This derivative, which looks like just a derivative for single variable calculus, right? But then now we are considering the function of two variables. Okay, well, but we still have this symbol appear again. So then what is the difference between the two cases? Single variable calculus, we have this df dt, no problem. But then this is now I have a two variable calculus, but then I define this so-called total derivatives, df dt, having the same symbol. So what is the difference? And also, remember in multi-variable calculus, we can always still take the partial f partial t. Then what is the difference between partial f partial t and df dt in two variable calculus? So these are the two questions that we just need to be careful. So then I use this example to try to illustrate the idea. So we consider a scenario. Okay, so suppose there's an airplane. Okay, it flies from Norway to Italy. Okay, from Norway to Italy. So first of all, you know that so okay, let me finish this sentence also. So it takes off at 5 a.m. and suppose it arrives at 8 a.m. Okay. Fly. It takes off early in the morning. Okay, 5 a.m. and it arrives at 8 a.m. So then I want to ask the following question. So suppose the airplane carry a temperature sensor. Okay, it can measure the temperatures of the air. Okay, as it flies. So how does this temperature T, okay, measured by this airplane change as a function of time? So there are actually two factors that we are considering. So first of all, the temperature will be rising as a function of time because it's moving. So it starts from a place that relatively closer to the North Pole and then move closer to the equator. Right? So that's why the temperature should be increasing because it's getting closer and closer to the equator. And there's the second factor is that from 5 a.m. to 8 a.m. So at this time the sun is rising, right? So then we know that no matter where you are, you will feel that it's getting hotter. Right? So there are two factors that we need to consider before we can understand how this temperature measured by the airplane change as a function of time, right? Okay, so then here just some, of course, always have some simplification, right? So I just assume that this airplane move in this one dimension, okay, labeled by X. Okay, I don't consider whether it's going up or down. Okay, so and then I assume that as I said, because the sun is rising, right? So within this time interval, okay, I assume that the temperature at every point on the map rise. So I don't care about the local variation of the weather in different spots, but I just assume that for the whole entire region, okay, the temperature increase as a function of time because the sun is rising. So and then I just assume that the velocity of the plane is v. Okay, you can just treat that as a constant. So now the temperature T measured by the airplane is a function of two variables. One is X, the other is T, time. Right, so the X is the position of this airplane, right? And the other is time. So then I represent this temperature, capital T, right, as a function of this X and this small t. So how does it change with respect to time? So then this is a key question. Now we are looking for change, then that means we are looking to calculate some derivatives. So are we looking for partial derivatives or the total derivatives? So then that's the key questions here. So the key questions is that in this case, we are looking for the total derivative because we are considering the both variables. So if I write down the total derivatives of this temperature, okay, with respect to time, then I have two terms. So the first one is partial capital T partial X times dx dt. And then the second one is just partial capital T partial time. So the first one is due to the change in the position of the plane, right? And then the second one is due to the change in time. So that means the first one is due to the fact that is moving closer and closer to the equator, right? And then the second term is due to the fact that the sun is rising, right, as I labeled it here. So now the thing is that the airplane position x, so in fact it is also related to time, right? Because position is a function of time, x equals vt, right? So then that means although it looks like we do have two variables, x and t. However, one of them, the position, we call that dependent variable. It's not really an independent variable because x itself also depends on time. So then in this sense, you can say that the temperature is in fact a single variable function, right? Because temperature is a function of x and t, but then x is also a function of t. So then that's why we have this total derivative. In fact, this is one of the example of composite function, okay, because you have a function depends on some variables, but then that one or more of the variables depends on some other variables. So a remark here is that if we neglect the existence of the airplane, okay, so but we just want to know the temperature distribution of the flight path itself, right? So what does that mean? So that means we put the temperature sensor at every point on this line, so on this along this path, right? And then we measure temperature at every point at every time steps. Then in that case, you truly have a two variable function. You have two independent variables. Right? In that case, x does not depend on time, or x can be anywhere that you pick. Right. So then for this paragraph, we just repeat what I just said. Right. So if I want to measure the temperature function measured by the airplane, right, so then x is no longer referred to any arbitrary point that you pick. Right. Instead, it only represents some particular position. Right. And then there are the temperature has two variables, but there's only one independent variable. This is known, as I already mentioned, this is known as the composite function. So geometrically, how do we represent the difference between partial derivative and total derivatives? So suppose I express this function of two variables, okay, in the conventional way. So again, I'm going to imagine that I'm going to draw a curved surface, right, in this xt capital T space. Right? I will draw a curved surface. Then the partial derivatives of either x or t will be the derivative along the two axes, right? But then the total derivative t will be along some lines. So the partial derivative with respect to x, let me just label it, is the derivative the partial derivative along x-axis is the derivative along this direction. And then the partial derivative for t is the derivative along this direction. Of course, I might not, maybe I should not use the word direction because it's not really talking about two-dimensional space, right? But in this sense, is that if I have this representation, you know what I mean, is that one is along the x-axis and the other is along the t-axis. That's the geometric meaning of the two partial derivatives. However, if I'm taking the total derivatives, then I'm taking the derivative, okay, along some lines like this. Okay. And then the slope of these lines, whether this line is like this or like this or like this, depends on the velocity of your airplane, right? Because if your airplane has a very high velocity, then maybe you are on this line. If your airplane has a very small velocity, then maybe you are on this line. So then here you can see that I'm trying to introduce one new concept, is that in the first minute of this lecture, I'm talking about two different partial derivatives, but along the x direction and then along the y direction. So that means that whether I cut it along this axis or along the other axis. But you could imagine that I could make my cut at an arbitrary angle. So it's neither partial x or neither it's neither partial x nor partial y. It's somewhere in between, and that is actually known as the directional derivatives, which I'll talk about next time. Okay, so I think I'm running out of time, and I think I'll just stop here for today. So if there's any questions, you are welcome to ask now. Okay. So actually, I want to ask, so 2041, I believe most of you are taking 2041. So do you know the midterm for that yet? When? (22nd) 27 October. Okay, 27. Any other courses that you have midterm? Is it 2061 or no?